This video is for Module 5, Part 3, and includes a discussion of measures of spread or variation. Okay, let's go ahead and get started. So there are additional characteristics for a set of measurements that are of interest other than just the measure of location. Here we are going to discuss measures of spread. So if we consider again a dot plot of the income levels across the state of Minnesota, we can see that original dot plot here is described under Situation 1. The average income across the 87 counties is $57,350. And we can see that the spread or variation in that distribution here on the screen. In Situation 2, we have exactly the same average at 57,350, but this distribution is not nearly as spread out. It has much less income disparity. So that is an additional characteristic that statisticians worry about, not just measures of location, but also measures of spread. Okay, the language used for measures of center is very consistent. So people use words like mean or average and median. However, when we're talking about variation, there are a variety of terms that get used. For example, spread, consistency, disparity, risk, all of those in a statistical sense or context refer to variation. So here we are going to discuss the range, the interquartile range, the mean absolute deviation, and then the standard deviation. And we're going to do that again for the household income levels across the state of Minnesota. So that data is provided here on the screen for the 87 counties in Minnesota. So let's talk about first the measure of spread being the range. So the range is easy to compute, and it's also easy to understand. However, it is very limiting in the information it provides about a set of measurements. The range is simply the maximum value in the dataset subtract the minimum value in the dataset. So if we have our percentiles, that's just going to be the 100th percentile is the maximum value, 93,151. And we're simply going to subtract the 0th percentile, or the minimum value in the dataset, which is 42,439. So that range, the range value for this data is right around 50,000. So the interpretation here, interpretation for the range, is simply the distance between the poorest county's household income and the richest county's household income. So it's just that distance between the smallest value and the largest value in our data set. So a couple of notes about the range. The range is not used as a measure of spread by statisticians. So even though it is easy to understand and it's also easy to compute, it is not a reasonable measure of spread for two reasons. Number one, the range only uses two values in the entire data set, and it ignores all other values. So in this distribution, all but two of these observations are ignored. So we don't worry, that's not a good idea. So for example, one would never find it acceptable to use only two values when computing a mean. And statisticians feel similarly that it isn't reasonable to use only two values to compute a measure of variation. Furthermore, the range is directly and adversely affected by outliers. So by definition, the range uses the smallest value in the dataset and the largest value in the dataset. And if there's any outliers present at all, they're going to be on the edges. So for that reason, the range is directly impacted by outliers. So for those two reasons, we don't use the range as a measure of spread. At least statisticians don't. A couple of questions about the range. So what is the smallest possible value? Well, the range is always going to take the largest value minus the smallest value. So the range is, the smallest possible value is going to be 0. The range cannot go below 0. I'll let you try to answer question 2 here. Okay, measure of spread, the interquartile range. So John Tukey, here's a picture of John Tukey over here. He was the inventor of the box and whisker plot. He used an idea called the interquartile range, which the interquartile range on a box plot is just how wide the box is. Now what we do to compute the interquartile range is we truncate or ignore the lower 25% of the data and the upper 25% of the data. So that information or those values get truncated. Now for that reason, the interquartile range is not adversely affected by outliers, because any outliers down here on the lower end or any outliers on the upper end will get truncated off. After truncation of the lower and upper 25%, we simply take the range of what remains, and that's called the interquartile range here. So it is simply the 75th percentile minus the 25th percentile. And you can see that the interquartile range is going to contain the middle 50% of the measurements. So the interquartile range is a neat little idea, but it is not used in practice very much. It's certainly used in the construction of box plots, but beyond that, the interquartile range is not a widely used measure of spread. Here's the calculations for the interquartile range for our data. We can just see that we're using the 75th percentile, and then we subtract from that the 25th percentile. Okay, so what do statisticians do if we don't use the range and the interquartile range is not a widely used measure? What we do to measure variation or spread is consider the distance to the center. Okay, so there's the income levels for Minnesota. The darker the red, the more they are below the average, and the more or darker green, the more they are above the average income levels. So you can see that for Minnesota anyway, income levels around the Twin Cities, kind of the outer edge or the suburbs of the Twin Cities, tend to have fairly high incomes. And then up here in northern Minnesota, there are some of the counties that are pretty low. These around, kind of surrounding the Twin Cities, kind of out a little bit further, would be kind of typical values in terms of income. Now for our discussion here, instead of working with Minnesota, I'm going to work with Rhode Island, and Rhode Island only has 5 counties. And instead of using their real data, I just made up 3 different situations for fictitious data for Rhode Island. So situation A, or data set A, has income levels that are all the same. So suppose all 5 counties had income levels right at 60,000. Data set B had income levels at 60,000 for 3 of the counties, but then I have one county at 40,000 and one county at 80,000. And data set C has one county each at 40, 50, 60, 70, and 80,000. 3 different situations. This situation A, or data set A, is going to have the least amount of spread. Okay. And data set C is going to have the most amount of spread when we consider distance to center. We will note that data set B and C actually have the same range. Okay, but when we measure distance to center, data set C is going to have more of that compared to data set B. Okay, so let's get into a discussion about how we measure distance to center. What we do is create what is called a residual. A residual, it is sometimes referred to as a deviance, is simply defined to be the distance between a data point and its average. So if we consider data set A, we have 5 data points. The average of these measurements is at 60,000. So the residual for this first point is simply going to be 60,000 minus 60,000, which is going to give me a value of 0. Now because all 5 values sit right on top of the average here, all of my residual values are going to be 0. Data set B, again, is going to have an average at 60,000. This value down here at 40,000 is going to have a residual of negative 20,000. So again, a residual is simply the data point, which is 40,000, minus the average, which is 60,000. That's going to give me a residual of minus 20,000. The point up here at 80,000, so for the residual for that point, I'm simply going to take 80,000 minus the average, which is 60,000, and I end up with a positive 20,000. Now when I compute a total of these, so if I get the total of all of the residuals, so I'm going to use that as a measure of total distance to the center, you can see that I get 0 when I add all of those residuals up. Let's consider data set C. So again, I have the 20,000 away. This county right here is going to be 10,000 away from the mean. So its residual value is negative 10,000. The value at 70,000 is going to have a positive residual value of 10,000. And then again, the positive 20,000. And again, when I sum these up, you can see that I'm going to get a value of 0 here. Okay, so no matter the situation here, when I add up the residuals across all of the observations, I get a total that is equal to 0. The canceling out of the negative and positive residuals is not unique to just these situations that I've created here, but happens with all data. If you recall, the average is the balance point in the distribution. When the residual values are summed across all observations, then that total is going to be 0. So all of the negative residuals will get canceled out by all of the positive residuals, and you're going to get a sum of 0. So this is true, again, in any situation. If you were to add up all of the residuals, you're going to get a total distance of 0. I want to compute a total, though, because my goal is to figure out the total distance to the middle. So here I'm using a measure of spread that considers distance to middle, and I want to get a total of that. But I can't use just a residual because of the canceling out of the positive and negative residuals. So we have two options to get rid of negative values. One is the use of absolute values, and the other is the use of squaring. So either one of those options are acceptable when trying to figure out a total quantity or a sum of the residuals. So here you can see that the sum is just of the absolute residuals, and then the other I'm going to square each residual. Squaring certainly gets rid of the negative value, and I'm going to add them up. Okay, let's talk about the mean absolute deviation then. The mean absolute deviation, or the mean absolute residual, is denoted by MAD, and it's computed as follows. It's just simply the average of the absolute residuals. So that's pretty intuitive. The absolute value will get rid of the negatives. Okay, so up here, if we're looking at this situation right here, it's just going to get rid of this negative value here on the negative 20,000. The one on the right, the positive residual, is already positive, so taking the absolute value there is just going to keep it positive. But it's going to flip this negative 20,000 to a positive 20,000. And that's what I want, because I just want to know distance to the middle. I don't really care if it's below or above, but an absolute value can be used to compute the distance. So if I do that for, let's say, data set B, that's the one I was looking at there, the negative 20,000 becomes a positive 20,000 when I do the absolute value. And then when I get a total down here, I'm going to end up with 40,000. I have 5 observations, so 40,000 divided by 5. The MAD here for data set B is going to be 8,000. So again, that's just the mean absolute distance, or excuse me, the mean absolute residual for data set B is about 8,000. If I do that on data set C, add them up again, I get 60,000. There were 5 observations, so 60,000 divided by 5 gives me a mean absolute deviation of 12,000 for data set C. The interpretation is here. Notice that the mean absolute deviation for data set A is 0. Okay, and that is the reason that is because data set A does not have any spread. So if we go back up here and look at our data set A, you can see that it doesn't have any spread in it. All of the values are stacked exactly on top of the average, so all of the residuals are 0. If I sum them up and divide by 5, I'm still going to get 0. So when the mean absolute deviation is really small, it means that you don't have much spread at all in your data. Okay, so let's talk about when I square the residuals. So when I square the residuals, I'm actually doing a calculation for the standard deviation. So here are the calculations again for data set A, data set B, and data set C. So I'm going to take the negative 20,000 here, and I'm going to square that residual, okay, which gives me a very large number here. So that 400 billion, I guess. I'm going to take the positive 20,000 and I'm going to square that as well. So here I'm squaring all of the residuals. That gives me another 400 billion. And then I'm going to create or obtain a total here. So 400 billion plus 400 billion is, I guess, 800 billion. And I divide that by 5, I get 160 billion. Okay, so this would be the average distance when I use squared residuals. For data set C, it's going to be slightly larger because, again, I have additional distance to the center for those two observations. The one at 50,000 and the one at 70,000 is going to contribute some more to the total distance to center. So these quantities right here, this average and this average, are called the population variance. Now what we do when we calculate this, and we have various reasons for doing that, and they're described here in this paragraph. But what we end up doing when we calculate the variance is not use the number of observations, but we use the number of observations minus 1. So here, instead of using 5, I'm going to be using 4. Okay. And the other thing that you're going to recognize is that these values are very, very high. I had incomes around 40,000, 50,000, and 60,000, and my average distance to the middle here is 160 billion. Likewise, for data set C, it's at 200 billion. Now, the reason these numbers are so large is because I squared those residuals. And when I have a fairly large number and I square it, that number becomes very, very large. So it turns out that the variance is actually not on the same scale as my original data, but it's on the squared scale of my original data. So to alleviate that problem, I just simply take the square root of the variance. So taking the square root of this will put that back on the original scale for me. So this squaring right here, this term right here, okay, messes up that scale. And the way to fix that is to take a square root of it when I'm done. And that's the standard deviation. So let's look at the standard deviation for data set A. Standard deviation for data set A, again, is going to be 0. Okay. And it's 0 because data set A does not have any spread in it. Data set B, when I use the standard deviation, is at 14,000 now. So the average distance to the middle under data set B is 14,000. And for data set C, it's slightly larger at 15,000. Notice that the standard deviation is indeed on the same scale as the data here. So this is dollars. That 250 billion that I have inside of that square root is on the dollar squared scale. So that's why we're taking that standard deviation. Okay, so standard deviation is a bit more complicated and involved. It has formulas that are a little bit more messy. But intuitively, the standard deviation just simply measures the typical distance each observation is away from the average. So here, let's just suppose I have 3 students, a 19-year-old, a 20-year-old, and a 21-year-old. And I ask you about how far away is the students from the average. The average here is at 20,000. Or excuse me, my average is at 20. You can see that they're about 1 away. And indeed, the standard deviation of these 3 measurements would be 1. So even though it's kind of messy up here with the formulas, intuitively the standard deviation hopefully makes sense. And again, those are 2 measures of spread that we use when we're looking at distance to center. So just some overall comments before I get into how to calculate these in a spreadsheet. So the range should not be used as a measure of variation. I mentioned that. The most common measures of variation are mean absolute deviation and also the standard deviation. The mean absolute deviation and also the standard deviation cannot be less than 0. So if I have a small value for standard deviation, that means I have less variation. And if I have a large value, that means I have more variation. One misconception about measuring variation is the following. Measuring distance to the middle is different than measuring the gap between values. So the following data here that I've presented has a consistent uniform pattern, and it has small gaps between each value. Okay, However, this data right here is not going to have a small distance to the middle. I have 60,000 here, and I stretch clear down here to 40 and clear up to 80, and I got a lot of values kind of spread out throughout there. So that's actually going to have a fairly large distance to the middle. So this data set here is going to have a large standard deviation. Even though the data are uniform and the gaps are pretty small, okay, the standard deviation is not measuring those gaps between the observations, but it's measuring that distance to the middle. So when you think of standard deviation or mean absolute deviation, I'd like you to think about these arrows that are pointing back to the middle, not the gaps between the observations. Okay, so how do I calculate these things in a spreadsheet? Well, there's two formulas that can be used. The first is just for the mean absolute deviation. Simply type AVEDEV and then just highlight the cells that you want to compute the average or the mean absolute deviation of. You could also give this a named range and then use that in place of the cell designations there. For the standard deviation, I just use the function stdev. Here I'm going to use a pivot table. So a pivot table can be used to compute the standard deviation. Pivot tables are nice when you have several summaries that need to be computed here. So here I want to calculate the average household income for Minnesota, Virginia, and Wisconsin. I want to get the standard deviations. I also maybe want to get the counts. How many counties or how many measurements do I have from each of those states? So if I want to get a bunch of summaries, the easiest way to do that is through the use of pivot tables. So when I'm building or constructing that pivot table, I want to specify state in the row box here. I want to specify 4 instances of household income. So here I'm getting the median, it looks like. I'm getting the average as well. I'm getting the standard deviation. And then I'm also getting a count. And then one thing that I often do is I'll put state in the filter box and then deselect blanks here so that I don't have that blank row when I construct that pivot table in Google Sheets. So if you set up a pivot table with the specifications, what you'll get is a nice little table of summaries as I have here on the screen. So here we can see that I have the 3 different states, Minnesota, Virginia, and Wisconsin. I got the medians. So again, as we said earlier, the medians are pretty similar. Got the averages here. I got the standard deviations, and then also the counts. Here's a graphic of those 3 distributions. We looked at this earlier, but just shown here so that you can see, kind of visualize what's happening in those distributions. And here are a set of questions that I'd like you to answer. Just about those summaries that we had up above. And then also information about, do the 2 measures of center agree? Which state has more income disparity? And then how do these relate to a CDF plot? Okay. That does it for Module 5, Part 3. Thank you.